Okay. We completed the meteor shower, and today we have to start with nuclear science, nuclear physics. Before we begin nuclear physics, can someone tell me what is meant by nuclear fission reaction? So, what is mean by nuclear fission reaction? There is a video. The video is lagging. Is it clear now? Is there a lag in the video? Can someone confirm if the video is good? Okay. I think it's from the user side. It's there for the past 2 days. Okay, I'll ask them to reconnect it. I've told the technical team here. Till then, we'll resume with the classes. I don't want to waste time because we are already starting 5 minutes late. So all the election campaign crowds here. Okay. First, the process of nuclear fission. It means a heavier nucleus breaking up into two or more smaller nucleus. That's called as nuclear fission reaction. Or otherwise, you can say a single atom breaking down into two or more smaller atoms. That's called as nuclear fission reactions. How about nuclear fusion reaction? I said nuclear fission is breaking off a large nucleus into smaller nuclei. That's called as nuclear fission reaction. How about nuclear fusion? What is nuclear fusion reaction? Nuclear fusion reaction. Small nuclei combine to form large nuclei. Good. Video lag ஆகுதாமே என்னன்னு பாருங்க நான் வரைக்கும் கண்டினியூ பண்றேன். Okay, smaller nuclei fusing to form heavier nuclei. It's called as a nuclear fusion reaction. So what is the main element that undergoes nuclear fission reaction? The main element that we know that undergoes nuclear fission reaction, can someone say? Important element that undergoes nuclear fission reaction. This is all brushing up your school physics lessons. Yes, uranium. Good. Other than uranium, uranium 235, more precise. Yes, okay. Other than that, thorium. Good. Plutonium. Good. Okay, these are the three elements which I wanted you people to remember. See here in the periodic table. First there is thorium, and after a gap we have uranium, and after a gap we have plutonium. We are going to talk about thorium, uranium, and plutonium. These three are called as tricolors of Indian nuclear program. So you can note down thorium space uranium space plutonium. You can write down in the same order. First it's thorium. When you add atomic number, it becomes uranium. When you add atomic number, it becomes plutonium. Thorium, uranium, and plutonium. These are called as tricolors of Indian nuclear program. Coming to the next one. Did we talk about an effect called as mass defect? Did we talk about mass defect? Can someone confirm if I gave an idea about the mass defect earlier? Mass defect in nucleus. Did we talk about mass defect? We have a lesser number of people here. Please participate so that it feels little interactive. Did we talk about something called as mass defect? Okay. So when we were talking about the formation of elements inside the star, I told you iron is the most stable element. That is, iron nucleus is difficult to break. That is called as binding energy. So if I'm going to track binding energy, if binding energy is plotted on the x-axis and the binding energy per nucleon, that is particles present inside the nucleus, if I'm going to plot this, in this case, the graph will go like this. It will slowly increase, it will reach a top point and then it will decrease. The point where the binding energy is maximum, it is for iron, Fe 2656. So iron has the maximum binding energy, wherein strontium, thorium, uranium, these elements have lesser binding energy. We are talking about binding energy, a core physics concept. It can be found in your NCERT book also. Hydrogen has lesser binding energy and uranium has lesser binding energy, which means if the binding energy is lesser, the atom can be easily broken, which means hydrogen can be easily broken, uranium can be easily broken. That's why we have hydrogen bomb and then we have atom bombs. That's based on uranium. Hydrogen bomb and atom bomb, wherein we do not have bombs based on other elements. The core reason is the nucleus do not disintegrate easily, creating a large amount of energy. So this is called as binding energy. I'll give you the basic definition for binding energy. You can write it down. Binding energy is the energy required to break a nucleus. This is layman's definition, energy required to break a nucleus, or you can say energy required to remove nucleon from an atom. This is called as binding energy. So what does it mean by nucleon? Anything that is present inside nucleus is called as nucleon. Protons, neutrons, or any other particle that's present inside the nucleus, it's called as nucleon. Anything that is present inside the nucleus, it's called as nucleon. So energy required to remove a nucleon from a nucleus is called as binding energy. Now, why do we talk about binding energy when we come to nuclear fission reactions? You understand? I'm going to tell you an example. This is not exactly the same, but I'm going to give you an example. We have helium-24, which means helium will have 2 protons, 2 neutrons. That is, the nucleus of helium will have 2 protons and 2 neutrons, and it will have 2 electrons. This is what the atomic numbers means. 2 protons, 2 neutrons, and 2 electrons inside. Let's say for illustration purpose, let's say the mass of one proton is 2 kilogram. This is exaggerated value, I'm saying for example. Let's say the mass of one neutron is 2.1 kilogram. Mass of one proton is 2 kilogram and the mass of one neutron is 2.1 kilograms. So in that case, what will be the mass of this nucleus? Can someone calculate what will be the mass of this nucleus that has 2 proton and 2 neutron? Can someone answer here? What will be the mass of this nucleus? The nucleus of helium-24. Should be 8.2. Okay, because 2 into 2 is 4 and 2 into 2.1 is 4.2. It should be 8.2. So the theoretical value should be somewhere close to 8.2 kilogram. But on actual scale, this will be lesser. This will be somewhere close to 6 kilogram, for example. So there is a difference between the calculated value and the actual value. That is, we have a 2.2 kilogram deficit. This is called as mass defect. Good. So where did this mass go? The mass is stored as energy. You remember the Einstein's mass energy relation? E equals to m into c square, mass into velocity of light square. So any nucleus that has a lesser mass compared to the theoretical mass, it means it is stronger. It has more binding energy. Write down one thing before we reconnect the call, that is stability of a nucleus. Is proportional to binding energy. This is one definition, or you can say stability of a nucleus is proportional to mass defect. You can say it both the ways. Write this for now. Or even we notice that there is a lag. Yes. I understand there is a video problem from our side. So we are trying to reconnect. Please stay online. We'll disconnect and then we'll connect again. You people please stay online in the meeting. Reconnect பண்ணுங்க.
You are in the meeting now.
I hope the video is clear now. One guy here, he has asked, the Asiatic cheetah has asked, how the atom will be more stable when there is more energy defect or when there is more defect. To understand, when something has more mass defect, it means more energy is stored between the nucleons, which means we have to spend a lot of energy to break it. Greater the mass defect, greater is the inherent or stored energy. Is it clear? Asiatic cheetah? Do you get it? Yes, stability is proportional to binding energy per nucleon. Vamshi, yes, stability is proportional to binding energy per nucleon. If something has more binding energy, when something has more binding energy, it means it has more mass defect. When there is more mass defect, it means the mass defect into C square. The equivalent energy is stored inside the nucleon, which means you have to spend more energy to break the nucleon. Mass defect is del M. That is the difference. The 2.1 kilogram is mass defect. So I have to put 2.1 kilogram into 3 into 10 power 8 the whole square. If I solve this, I'll get a value. That much of energy is stored inside the nucleus in form of energy, not in form of mass, but in form of energy, which means efficiently, effectively, I have to spend that much of energy to break the bonding that keeps the nucleus together. Generally, it's not calculated in kilogram, it's generally calculated in atomic mass unit, AMU. So the deficient mass into C square. Asiatic cheetah, you get it? Vamshi, you get it? Is it clear? Can we go to the next one? Can someone confirm if it's clear? Yes. Vamshi, your doubt is clear? Stability is proportional to? Yes. Okay. So protons and neutrons combine to form nucleus and the mass defect is converted into equivalent amount of energy. You can write on this point if you want. This is called as binding energy and we have already written this point. Binding energy is proportional to stability against disintegration. When something has more binding energy, it's difficult to break it. By the meantime, did you people get a message in your Telegram channel? Did you check it? I posted a mains answer writing practice question along with the sources. Yes. Please attempt the question after completing the nuclear physics. We'll be completing today. We'll have better understanding. Try to write the question and then send it to the email address attached there. And few of you have sent answers earlier. I'm correcting them. I'll send you shortly. Good. We'll go to the next one. We're talking about this is the binding energy curve which I was talking about. This is given in your NCERT. You could see for hydrogen it's lesser. There are few spikes, greatest for iron, and then again it decreases. Keep in mind. Coming to nuclear fission reaction. So breaking up of nucleus of heavier atom into fragments is called as nuclear fission reaction. Which elementary particle initiates the nuclear fission reaction? Can someone answer? Which initiates the nuclear fission reaction? Is it a proton or is it a neutron or is it an electron? Which elementary particle initiates the nuclear fission reaction? Okay, it's common to think that it's electron. Yes, it's actually neutron that causes the nuclear fission reaction. So before that, I'll ask a question which was explained earlier. Neutron, proton, and electron. 1, 2, and 3. Which one has the highest mass? Which one is heavier? Which one has the highest mass? Out of these three elementary particles, which one has the highest mass? Neutron. Sri Lakshmi, yes, good. Electrons are greater than protons, is greater than neutrons. Yes. When we are talking about the beta decay that happened during the Big Bang, we told neutron breaks up into protons and electrons. That's how initially protons and electrons were formed. They were formed by beta decay from the neutrons, forming protons and electrons. Good. So neutrons are the heaviest, and also we would have studied about the properties of neutrons. One familiar property, that is, it is neutrally charged. That is, it has no net charge. This is neutral in nature. When something is neutral, it's not necessary that it should be less reactive. Something is neutral, that is electrically neutral. It doesn't mean it is going to be calm. Understand, neutrons are stable inside the nucleus. Two important lines. Neutrons are stable inside the nucleus and they are highly reactive outside the nucleus. Neutrons are stable inside the nucleus, that is less reactive, and they are highly reactive outside the nucleus. The entire fission reaction is carried out due to neutrons. Are we good to go? Clear? Neutrons are stable inside the nucleus. They are unstable and highly reactive outside the nucleus. Now, on how it breaks, how a nucleus breaks, there is a familiar model called as a liquid drop model. What happens when a liquid drops on the surface? It breaks into multiple components, correct? It breaks up into smaller components. Many new components will be formed. Similarly, when a nucleus breaks, it becomes ellipsoidal in shape, it forms a dumbbell shape, and then it forms two smaller elements with emission of a lot of neutrons. This gives you precisely what happens during nuclear fission reaction. You can note this down.
Received Paytm payment or
Clear? Can we go to the next one? Good. Coming to the next one. We're going to talk about uranium. When nuclear fission reaction happens, see first a neutron, it has to go and strike uranium. Generally we write uranium 235. So this uranium 235 breaks into barium, krypton, and it releases 3 more neutrons plus a lot of heat energy. This is the general reaction for nuclear fission reaction. One of the equations, in fact. Uranium breaks up into barium, krypton and releases 3 neutrons, and it releases a lot of energy because of a single neutron. Good. So this is not the only possibility through which uranium can break. There are few other possibilities. For example, sometimes uranium 235, when it's hit by a neutron, it may break into xenon and strontium. This is also possible, and this will emit around 2 neutrons and a lot of energy. This is one more equation. Uranium, it may split into xenon and strontium with 2 neutrons and a lot of energy. Either way, it will emit more neutrons. Sometimes it emits 3 neutrons, sometimes it emits 2 neutrons. So on an average, what is the average of 3 and 2? It is 2.5. So note down one additional point. Average number of neutrons released per fission is 2.5. I repeat, the average number of neutrons released per fission is 2.5. And one more thing, average energy per fission. Average neutron produced per fission is 2.5, and additionally there is one more point. Average energy per fission is 200 mega electron volt. Average energy and average neutrons. Good. Now, let's take a look at this reaction. See how many neutrons we are providing? 1 neutron. How many neutrons it has formed? 3 neutrons. So I have provided 1 neutron and it forms 3 neutrons. Is it possible that these neutrons go and hit one more uranium 235 and then causes further fission? This is possible, right? So that's called as a chain reaction. And in chain reaction, you have 2 different types, that is controlled chain reaction and then uncontrolled chain reaction. 2 types of chain reactions, controlled chain reaction and uncontrolled chain reaction. So where does controlled chain reaction happen? That is uncontrolled number of neutrons. Where does an uncontrolled chain reaction happen? Can someone tell? Easy question. Where does an uncontrolled chain reaction happen? Yes, bombs, atom bombs. Good. Where does a controlled chain reaction happen? Where does a controlled chain reaction happen? Yeah, nuclear weapons, they have uncontrolled chain reaction, and nuclear reactors, they have controlled chain reaction. Good. So this is an uncontrolled chain reaction. So For example, uranium forms barium, krypton, xenon, strontium, cesium, a lot of elements, and the number of neutrons, it keeps on increasing. Take a look at this. 1 neutron, it becomes 3 neutron, and again it becomes 9 neutron, and then it becomes 27 neutrons. So what is the series called as? 1, 3, 9, 27, it goes on and on. The number of neutrons keeps on increasing in geometric progression. Do you remember high school mathematics? We have arithmetic progression, geometric progressions. So write down 2 simple sketches. First thing, chain reaction. The basic definition is neutrons produced by nuclear fission causes further fission reaction. This is called as chain reaction. Neutrons produced by fission reaction, it causes further fission. This is called as a chain reaction. And then we have 2 types of chain reaction. First chain reaction is controlled chain reaction. Second is uncontrolled chain reaction. Why we call it as a controlled chain reaction? That's because neutron numbers are controlled. And here there is no control on neutrons. That's called as an uncontrolled chain reaction. Controlled and uncontrolled chain reaction. Where does this happen? Controlled chain reaction. It happens in nuclear reactors. Where does an uncontrolled chain reaction happen? Nuclear bombs. We are slowly building the lesson. So initially it may be a bit boring, but this is your basic. You should not skip this. You have an individual lesson for atomic physics in 11th and 12th. In chemistry book, you may not go through the entire part. So this will help you to understand better. And now, if I want to control this reaction, I have to control the neutron numbers. And also write down one more thing. Number of neutrons increases in geometric progression. During an uncontrolled fission reaction. So the number of neutrons increases in geometric progression during an uncontrolled chain reaction. Important. Coming to the next part. So if I control the number of neutrons here, the reaction will be controlled. Take a look at this. So a single neutron, it breaks and produces 3 neutrons, and 3 neutrons produces 9 neutrons, and then 9 neutrons produces 27 neutrons, and on and on and on. So which means the chain reaction is a self-sustaining process, which means only initiation is our responsibility, wherein sustaining, it goes on. First one, it's a self-propagating process. Please note down, it's a self-propagating and self-sustaining process. Now, if you want to reduce this reaction, we have to reduce the number of neutrons. Take a look at this on an imaginary scale. If I'm going to control these neutrons, then the reaction will become like this, correct? This is uncontrolled neutrons. If I remove the neutrons in the very first stage, then it becomes like this, which means this is still a chain reaction, because step 1, step 2, step 3, this is still a chain reaction, but happens in a controlled manner because the neutron number is kept in control. This is called as controlled chain reaction. Good. Coming to the next part, we are going to talk about nuclear reactors. One simple thing. The nuclear reactor, if you see the reaction that we were talking about, uranium-235, it breaks into barium plus krypton plus 3 neutron plus a lot of energy. So this heat energy, the heat energy that is produced during a nuclear fission, it's going to be tapped. We are going to pass water inside, and the water will take the heat and it will produce steam. And this steam, it will be used for driving a turbine. This is how a nuclear reactor works. So indirectly, this is a form of hydrothermal. It's a form of thermal energy. How do we create thermal energy? We burn a lot of water, and then we produce steam, and then using the steam we spin the turbine. So similarly, this is also one form of thermal energy, where the thermal part is extracted from nuclear fission reaction. A lot of heat produces steam in water, and the steam is used for driving the turbine. That's how it works. Good. And now I have a doubt. The entire reactor, it's going to use fuel. The first component is fuel. What is used as fuel in India? Can someone say, what is the nuclear fuel that is used in India? Simpler question. What is the nuclear fuel used in India? Yes, good, uranium. Uranium-235. Good. So we are saying it is uranium-235. Wherein, do we have enough domestic supply of uranium? Do we have enough domestic supply of uranium? No. So what do? We generally import it from, mostly imported from Russia, Canada, Australia, from different parts of the world. We import uranium. And when uranium is imported, it has two components. We call it as yellow cake generally, because it appears yellow in color with a lot of spores. It appears like a sponge. We call it as yellow cake or uranium ore. This uranium ore, this will contain two components. All the uranium ore, it will have two isotopes, uranium-235 and uranium-238. Uranium-235 and uranium-238. Now my question is, we are going to use only uranium-235 and not uranium-238. What will be the concentration of uranium-235 in terms of percentage? Let's say out of 100%, what will be the uranium-235 concentration? What will be the concentration of uranium-235 in terms of percentage? What will be the concentration of uranium-235 in terms of percentage? Let's say out of 100%, what will be the concentration of uranium-235 in terms of percentage? Let's say out of 100%, the concentration of uranium-235 in terms of percentage? Can someone make a random guess? The uranium, out of the 100% of the uranium ore that we import, how much will be the uranium-235 that we utilize? Let's say, for example, we are importing 100 kilogram of uranium ore. This, how much will be uranium-235? Okay, one says 70%, 2%, 10%, 50%. Okay, good. The most astonishing fact about the nuclear energy, observe, 0.72%. This is the amount of uranium-235 present, wherein 99.28% is uranium-238, which means if I'm going to import 100 kilogram, I'll be getting somewhere close to 720 gram of uranium-235, which I can use it in the nuclear reactors. The rest of the uranium-238, it will form around 99.28 kilogram. This is the density of uranium-235 that will be present in uranium ore. Now, why we can use uranium-235 and why we cannot use uranium-238 while both of them belong to uranium? See, there are three types of neutron. I repeat, if you have missed the percentage, I'll repeat again. Uranium-235 is 0.72% and uranium-238 is 99.28%. Now coming to the neutrons, I told you neutrons are extremely reactive outside the nuclear outside the nucleus, wherein it's stable inside the nucleus. And we have three types of neutrons. Basics in your NCERT, we have fast neutron that are highly energetic. Then we have slow neutron. And then we have thermal neutron. Three types of neutrons depending on their energy. First one, the fast neutron will have energy, high energy somewhere close to 10 mega electron volt, wherein this will have somewhere close to 4 to 5 mega electron volt roughly. I'm saying only the approximate value for comparison purposes. This is not the exact value. Wherein thermal neutron, it will have around 0.025 electron volt, which means these thermal neutrons, they'll be traveling extremely slower, they have lesser energy, wherein slow neutrons, it is comparatively having more energy, and fast neutrons have extremely huge amount of energy. Three types of neutrons. I repeat, this value is exact, wherein these values are for comparison purposes. Fast neutron, slow neutron, and thermal neutron. And now coming to the part, why we do not use uranium-238 for nuclear reactors, wherein we use only uranium-235 to explain all the nuclear fission reaction. Understand one important fact. Both uranium-235 and uranium-238, both the uranium, it can undergo nuclear fission reaction actually. But the problem is, uranium-238, this will undergo fission reaction only if it is hit by fast neutron. Only if it is hit by fast neutron, wherein uranium-235, this will undergo fission reaction if it is hit by fast neutron, if it is hit by slow neutron, or if it's hit by thermal neutron. Any type of neutron, it will undergo fission reaction. Imagine if there is a last, you people watch cricket, right? So there is a last over where India requires 30 runs to win. Last over, 6 balls and 30 runs to win. So one batsman says, I can face only the fast ball, wherein I cannot face a medium pace ball or I cannot face a spin ball. Wherein there is one more batsman who says, irrespective of the type of ball, it could be a spin bowler, it could be a fast bowler or a medium pace, anything. I can smash 30 runs in the last over. So in that case, who causes the more mass destruction is the person number 2. So which one will be the most preferred? The person number 2, because the output is high. So similarly, uranium-238 will undergo fission only if it has fast neutron, if it is supplied with fast neutron, wherein uranium-235, it will undergo fission reaction under fast, slow, and thermal neutron, irrespective of the energy of neutrons. For this reason, uranium-235 is the most preferred atomic fuel throughout the world. Good. And now, coming to the fuel part. Atomic reactor is extremely complicated mechanism, while most of them are kept secretive, only few of them are given out, the prototypes and everything. So I'm going to explain in a very simplified way because the policies related to nuclear reactors and everything is more important than the actual working mechanism. First thing, we're going to talk about fuel. You could see here a person is standing here. This is a small scale Chernobyl reactor. In fact, this reactor is medium sized reactor, not even a large reactor. You could see person standing here and you can see a lot of slots here. All these are fuel rods. That is, we'll be filling fuel and then we'll be inserting it into the reactor core. That is called as a fuel rod. In case of fuel, in India, we use uranium-235 as fuel, and few countries they use low enriched uranium. So what is mean by low enriched uranium means? I told you only 0.72% is the concentration of uranium-235 present, but if you subject it to centrifugation and few other chemical processes, you can increase the concentration up to 2% or even up to 4%. This is permitted. Increasing the concentration of uranium is called as enrichment. So mostly in case of India, we use uranium-235 at its natural concentration, that is 0.72%, and few countries they use low enriched uranium. Good. And the major type of reactor that we use in India is called as Calandria reactor. It's a Canadian reactor. Calandria is the type of reactor that we use in India, most of the reactors. The fuel is uranium-235. And let's say the fuel rod is here. It has uranium-235 inside, and then a neutron is going to hit the fuel rod. What will happen? It will be subjected to nuclear fission reaction. It produces barium, it produces krypton, it produces 3 neutron plus energy, correct? Plus energy. And there will be multiple fuel rods. So before this neutron goes and hits the other fuel rod, first thing that we have to do is we have to reduce its speed. That is, the neutron has to be converted from a fast neutron to a thermal neutron, because this is formed by explosively by splitting up of nucleus, which means it will be extremely high energy. This will be a fast neutron. So the fast neutron, it has to be converted into a thermal neutron. That is, we have to reduce the speed for two purposes. First thing, it's easier to absorb a slow neutron, because we have to absorb the extra neutrons. It requires to slow down. Second important thing, only when the neutron is slow neutron, there will be more fission reaction that happens. That is, the reaction rate increases. For this purpose, we have to slow down the neutron from fast neutron to thermal neutron. And this process is carried out by a component called as moderator. Second component, moderator. So moderator, it converts fast neutron to thermal neutron. Why do we convert fast neutron to thermal neutron? For two reasons. First thing, easy to absorb. And second important thing, increased rate of fission. For these two purposes, we'll be slowing down the neutrons. And who is going to slow down neutrons? In case of India, we have two important moderators. First one, it is water. That is H2O. Or we have heavy water. That is water with the additional neutron. Deuterium dioxide, D2O. And in some cases, in few reactors, in older reactors, they used graphite or lead. Graphite or lead. These three are the primary moderators. Water, heavy water, and the graphite. We're going to slow down the neutrons. You could see here, fast neutrons they hit the moderator nuclei and they become slow or thermal neutrons. This is called as a moderator. And now, next thing, we have slowed down the neutron and we have to, the next thing we have to absorb the neutron. So, neutrons are absorbed by control rods. You could see here, these are the control rods. The concept is, if you're going to pull the control rod outside, the fission reaction will increase. If you're going to push the control rod inside, the fission reaction will reduce. So, these are the control rods of a reactor. Control rods. The purpose is to absorb extra neutrons. And create a controlled chain reaction. Why we are absorbing the neutrons? To sustain a controlled chain reaction. And in case of India, we use boron carbide, B4C. Boron carbide is used as control rod. Boron carbide is used as control rod. The interesting thing about control rods is after recent incidents, that is after the Fukushima reactor accident, most of the reactors worldwide, they are adopted with a newer technology, that is these control rods, they will be attached to an electromagnet. With all these control rods, they will be suspended above the reactor, half inserted into it by an electromagnet. So, once some seismic activity is detected, that is if there is an earthquake or tsunami type of activities that causes a seismic wave, the first thing it will do is it will deactivate the electromagnet. What will happen once the electromagnet is deactivated? The entire control rod, it will be immersed inside the reactor. So, the entire control rod, it goes into the reactor. So, what happens when the entire boron carbide falls into the reactor? All the neutrons will be absorbed and abruptly the chain reaction will stop. So, this is taken as a safety measure. Most of the reactors, and importantly the reactors in Japan, they have this technology. So, control rods plays the crucial safety role. Clear? And now, the next is, we have to talk about coolant or cooling system. Which means the cooling system takes the heat outside the reactor so that the steam is produced and then the turbine spins. So, in case of India, the moderator itself acts as a reactor. That is, we have a pressurized heavy water reactor, indigenous reactor developed by India, pressurized heavy water reactor. Most of the reactors in India are pressurized heavy water reactor, while other types are boiling water reactor, and we have few other reactors. Pressurized heavy water reactor, this uses moderator. In case of these reactors, moderator equals to coolant. That is, again H2O and deuterium dioxide. This will be used as a cooling system or coolant, and in some cases recently we have been developing liquid sodium. Liquid sodium, because the boiling point is somewhere close to 1000 degrees Celsius. For this purpose, we are using this to cool down the reactor. Liquid sodium. And then one last part, that is, we have to talk about neutron reflectors. Or or you can say the blanket outside the reactor. The nuclear fission reaction is happening inside the reactor. Good, even if it's in a sustained manner. I told you we have fuel rods, and then we have control rods. Everything is there, and we have moderator and coolant. When this is happening, there is still a possibility that some of the neutrons it can try to escape. That is outside the fuel rods. Some neutrons may be scattered and they may go towards the walls of the reactor, correct? And these neutrons, they have to be trapped without escaping. For that, we'll be covering the reactor with the neutron reflector. The function of neutron reflector, it is to absorb the neutron. What we will be using as neutron reflector, most of the cases, in Indian scenario, we'll be using uranium-238. Uranium-238, in many cases, it's used as neutron reflectors. Now the question is, why? Why we are not enriching uranium, and why we are using uranium-238 as a blanket or a neutron reflector? Can someone answer? Do people have any idea on why we use it? Yes, H2O and D2O are also acting as coolant. Sri Lakshmi, liquid sodium is also a coolant. So in case of India, moderator and coolant are same. That is H2O and D2O. Water at high pressure and heavy water. Both are used as coolant. Okay. So why we are using it as neutron reflectors? Because it does not react with slow neutrons. Good. Any other possible explanations? That's a good attempt. Your answer is correct actually. I'll tell you one more purpose hidden in it. Any other idea on why we use uranium-238 as a blanket around the fuel rods? Okay, it's available. Yeah, because we are importing a lot of uranium and we have a lot of uranium-238 left over. So we can cover it as a blanket. Good. It will convert the fast neutron, okay, back into the reactor. Okay. So the most interesting part about uranium-238 is, good, uranium-238, when it reacts with a neutron, good, let's say this is a slow neutron or thermal neutron in most of the cases because we have moderator. This will not undergo fission reaction, but it's possible that the uranium absorbs this neutron, correct? The uranium, it can absorb the neutron, but it may not undergo fission reaction. So what will happen is, it will be converted into plutonium-239, important one. So this process is called as artificial transmutation. Transmutation, creating a new element artificial by artificial means. It's called as artificial transmutation. Converting one element into other element by artificial methods, it's called as artificial transmutation. Clear? So one reason that India has not enriched uranium-235 is, this is the cause. We are utilizing the uranium-238 and we have been gathering a lot of plutonium-239. All these 5 or 6 decades of Indian nuclear program, we have been accumulating a lot of plutonium-239. Now the question is, why are we accumulating plutonium-239? Can someone answer? Any plausible logical explanation on why we are accumulating a lot of plutonium-239? Make random guesses, it's perfectly fine. Used in agriculture, yeah, yes, possible. There are few byproducts that can be used in nuclear medicines and reactors. Sri Lakshmi says it can be used in fuel. Good. That's the most important thing. So plutonium-239, this plutonium-239, It undergoes fission by fast, slow, and thermal neutron, which means plutonium-239 can be used as fuel in other reactors. For this reason, we have been accumulating a lot of plutonium reserves all these days. Good. You can note down this reaction here. Uranium being converted into plutonium. What I wrote was a simplified formula. This is the actual formula given in your NCERT. Electrons, positrons, neutrinos. Done. Can we go to the next one? NP is neptunium. NP is neptunium. Neptunium is formed as an intermediate product. This is not stable. Again, it decays into plutonium. This is highly unstable. It lasts for a few fraction of seconds and then it's converted into plutonium. Done. Coming to the next one, we are going to talk about India's three-stage nuclear program. I repeat, we're going to talk about India's three-stage nuclear program. Take a look at this. So when uranium, when it absorbs neutron, it's transmuted into plutonium, correct? Uranium, I think the color is not visible. Hold on. Yeah. So uranium, when it absorbs neutron, it becomes plutonium. So logically, what should happen when thorium absorbs neutron? What should be formed when thorium absorbs neutron? What should be formed when thorium absorbs neutron? Yeah, practically uranium should be formed, correct? Yes, that's called as India's three-stage nuclear program. We are going to talk about India's three-stage nuclear program. Can someone say what is the present stage that we are in? What is India's current status with respect to nuclear program? Are we in stage 1, are we in stage 2, or are we in stage 3? Random assumptions. Stage 1, stage 2, stage 3. Where are we right now? Asiatic Cheetah says first stage. Maheshwar says second stage. Okay. Shivapriya says first. Sri Lakshmi says second. Okay. Right now, we are in stage 1. I repeat, right now, we are in stage 1. So stage 1 is, it uses pressurized heavy water reactor. I'm writing the short form, PHWR, pressurized heavy water reactor. It's an indigenous technology. I repeat, it's developed by India. The fuel that is used is uranium-235. Along with that, we place uranium-238 also. So what is the byproduct that is formed? Byproduct, uranium-238 is transmutated into plutonium-239. So we have two components, uranium-239 and some other uranium-238 that has not transmutated. So once the reactor reaction is over, we have two components right now. Some of the uranium-238 that is converted into plutonium-239 and some other uranium-238 that has not undergone reaction. Right now, these are the byproducts. Clear? No doubt in this. Coming to stage 2. Stage 2. It's called as fast breeder reactor. The specialty about the fast breeder reactor is the fuel. It's going to be plutonium-239 because it can undergo nuclear fission reaction by a fast neutron, by a thermal neutron, and slow neutron. And along with that, we'll be keeping the uranium-238 that has not undergone reaction. From stage 1, the leftover uranium-238 will be keeping inside the reactor. And now, again, the byproduct. What will be formed as the byproduct? Plutonium-239 will break to produce a lot of energy along with a lot of neutrons, and those neutrons it made uranium-238. And again, this uranium-238, this will form plutonium-239. So one more atomic fuel is formed as byproduct. We are spending plutonium-239. At the same time, we are producing plutonium-239. Imagine you fill the car with 20 liters of petrol, you go home and check, you travel for 100 kilometers and then you check your petrol tank, again there is 20 liters of petrol. Won't it be nice for the present rate of the petrol that we are facing? 20 liters of petrol, 100 kilometers traveling, and then again 20 liters. So that's how it works. Basically, you are spending plutonium but breeding more fuel. But even though it looks like it's defying the law of conservation of energy, the amount of energy spent in producing the plutonium-239 is totally different because we have to add the stage 1 and stage 2 together. So back to the core part, plutonium-239 is fuel and plutonium-239 is the byproduct. This is the most interesting part about fast breeder reactor. Can someone tell me where is India constructing the fast breeder reactor? Where is India constructing the fast breeder reactor? Any idea? India is trying to attain the fast breeder reactor technology. Where is it constructing the fast breeder reactor? Interestingly, it's located in Kalpakkam. Kudankulam is power reactor. It's located in IGCAR, Indira Gandhi Center for Atomic Research, Kalpakkam. Fast breeder reactor is being constructed at Kalpakkam. And now, right now we are constructing it. This was supposed to be completed by 2019, then it was delayed to, in fact 2018, and then delayed to 2019, and then delayed to 2020, hit by the pandemic. There is no update about it in 2021. So right now we are constructing it. We are yet to attain criticality. So first question is, what is mean by criticality? So generally in medical terms, when we label something as critical, it means it's serious. Wherein in a nuclear reactor, attaining criticality means it is operating properly with a proper number of neutrons. That is, sustained, controlled chain reaction is happening. That's called as criticality. Wherein there is one more term called as subcritical. Subcritical means the reactor is not working properly. That is, lesser number. It is producing lesser number of neutrons to sustain the reaction. And then there is one more thing called as supercriticality or supercritical, which means the reactor has more neutrons and this needs to be controlled because this is not at all safe. The neutron number, it has to be controlled. So in newspapers, if you read that reactor is attaining criticality, it's not a negative term, it's a positive term. Criticality means it's functioning properly with a controlled chain reaction that's happening inside. Criticality is a proper positive term. wherein subcritical and supercritical are negative terms, especially the supercritical. When there is more number of neutrons, there is a danger of it exploding and causing uncontrolled chain reaction, for which the reactor should never attain supercriticality. Even if it attains, it has to be controlled instantly almost. Good. Please repeat, couldn't hear due to network issues. Okay, Sri Lakshmi, here again. When a reactor is functioning properly, when it is producing a proper number of neutrons, and the chain reaction is sustained and controlled, you call it as criticality of a reactor. If a reactor is critical, it doesn't mean it's serious. It means it is functioning properly. That's called as criticality. Coming to the next one, calling something as subcritical. It means it's producing lesser number of neutrons. The chain reaction cannot be sustained. That's called as subcritical, which means the reactor is going to shut down. And then supercritical. Supercritical means it's producing more neutrons. What happens when something produces more neutrons? There is a danger of it exploding or causing catastrophe. That's called as supercriticality. So in terms of nuclear energy, subcritical and supercritical are negative terms, wherein criticality is a positive term. When a reactor functions properly, you call it as criticality. Sri Lakshmi, is it clear? Can we proceed to the next one? Can you confirm? Yes. Coming to the next one, that is stage 3. So in stage 2, we have produced more plutonium from plutonium. That is using a fast breeder reactor. And coming to the third one, that is stage 3. Generally, we will be using advanced heavy water reactor. This is just a conceptual reactor. We are yet to construct it. Good. We are going to mine thorium. So the main reason for mining thorium is we have more thorium reserves. I'll tell you one statement. You say if it is true or false. India has the highest amount of thorium reserve in the entire world. True or false? India has the highest amount of thorium reserve in the entire world. True or ASWR means advanced heavy water reactor, Ashwin, but it's all conceptual. Yes. So India is the single country that has the highest amount of thorium reserve, somewhere close to 3,60,000 tons. 3,60,000 tons of thorium-232 is present, wherein uranium reserve, it's somewhere closer to 70,000 tons. Uranium reserve is much lesser. You may think this is lesser, but understand the amount of energy produced by 100 tons of uranium can be produced with 1 ton of thorium. Thorium is more energy intense. We'll talk about it later. You can write this alone. You can use these for your answer writing. The practice question which I have given. India has the highest amount of thorium reserve. Where are these reserves found? Can someone tell me where are these reserves found? The thorium reserves. Kerala, monazite sand, okay. Yes, Tamil Nadu, Kerala coast, good. Mostly the eastern coast, Kerala, Andhra, up to Odisha, and then in western coast, Kerala. These areas have the highest reserve of thorium. Till Odisha, there is higher amount. Even Chhattisgarh has some amount of thorium reserves. Good. For this reason, we'll be mining thorium sooner once we step into the stage 2 of the nuclear program. Now coming to the stage 3. Stage 3, I told you we are going to use advanced heavy water reactors. So ASWR, you can write down the abbreviation alone. You won't get questions based on this because this is just a conceptual reactor. We do not have the prototypes to learn. In this, the fuel will be plutonium-239 that is produced by stage 1 and stage 2. Along with it, we'll be keeping thorium-232. So what should be formed as byproduct? What should be formed as byproduct along with the atomic number? Can someone say what should be formed as byproduct? Uranium, good. Uranium is formed, but with one small change. That is, it produces uranium 233, not 35. It will produce uranium 233. Uranium 233 is an important atomic fuel because again it can undergo fission reaction under fast, slow, and thermal neutron. Any type of neutron, it can undergo fission reaction. So we'll be converting the thorium reserve present in the country into uranium 233. That is the idea. Shivapriya, what is mean by 1T inside? Yeah, I told you the amount of energy that can be produced by 100 tons of uranium, it can be produced from 1 ton of thorium. Like 1000 kilogram of thorium can produce energy equivalent to 100 tons of uranium, which means it's more energy intense. The density is more. Is it clear? Yes, yes. So this is called as India's 3-stage nuclear program. And right now, let's break few myths about nuclear energy. First of all, answer in terms of true or false, and then you can write down the sentences later. First, India built the first nuclear reactor in entire Asia. True or false? I'll repeat the question. India built the first nuclear reactor in entire Asia. True or false? India constructed the first nuclear reactor in entire Asia. True or false? Okay. Second question. No reactors in the world operate with uranium-233 as fuel. No reactors in the entire world operate with uranium-233 as a fuel. True or false? Just make the attempts. This is for learning. No reactor in the world operates with uranium-233 as fuel. True or false? Okay. One more question. India has not tested the prototype of fast breeder reactor. True or false? India has not even tested the prototype of fast breeder reactor. True or false? Okay. Good, good, good. And now, coming to 3 important things. First one, Apsara, located in Trombay, is the first reactor in the entire Asia built by India. First reactor in Asia. It might sound new. Yes, we built the first ever nuclear reactor in the entire Asia. And based on the purpose, we are going to divide the reactors into 3 types. Nuclear reactors, I'm going to divide it into 3 types. First is research reactor. That is a reactor that's going to be used for research purposes. And then we have power reactors. And then we have production reactors. What's meant by research reactor? Anything that's going to be used for research purposes is called as research reactor. Example is Apsara. Apsara is the best example of a research reactor. So we built the first research reactor, and you would have come across the fact that Tarapur is the first atomic power station. Remember, power reactors are used for producing electricity and supplying it to the people. So the first power reactor built in India was Tarapur, not the first reactor, first power reactor. First power reactor in India. That is Tarapur. If you get a statement saying Tarapur atomic power station is the first ever nuclear reactor in India, no, not at all. We had research reactors earlier. And this Apsara is important because this was decommissioned in 2009 and recommissioned in 2018. Right now, Apsara is functioning in an advanced or better form that's called as Apsara upgraded. Apsara U. Right now, Apsara is functioning even now, making it one of the oldest nuclear reactor in Asia. Apsara has been upgraded. It is functioning as Apsara U. This is current affairs from 2018, but still please read about it because we decommissioned in 2009 and recommissioned in 2018 for production purposes. And coming to the production reactors. Good. See, for production reactor, I'll give you one simple thing. What are the nuclear fuels that will undergo fission reaction by fast, slow, and thermal neutrons? So far, I've given you multiple fuels. What are the fuels that will undergo fission reaction by fast, slow, and thermal neutron with the atomic number? Can someone say? Please make an attempt. You can look at your notes and answer. Plutonium 239. Harini says, okay. Plutonium 239. Good. Then, okay, uranium 235 and uranium 233. Good. Yes. And now we have one more classification, that is uranium 238 and then thorium 232. So these are capable of undergoing nuclear reaction provided they undergo artificial transmutation. Am I correct? Even these two materials, they can undergo nuclear fission reaction, but only after transmutation. That is the case. So these are called as fissile materials. And these are called as fertile materials. Between power and production reactor. Yes. Sri Lakshmi, I'm coming to the point. Any reactor that converts a fertile material into fissile material is called as production reactor. That is, we are solely using it for production purpose, not for power generation. Production reactor. This is not power production reactor. This is material producing reactor. A reactor that converts fertile material to fissile material is called as production reactor. Sri Lakshmi, is it clear now? Yes, good. And one more point to remember. See, right now there is only one reactor in the entire world that operates on uranium 233. Keep this fact in mind. There is only one reactor, that is Kamini. Kamini is the only reactor that uses uranium 233 as fuel. Why countries are not using uranium 233 as fuel means it's extremely rare to find it. It's found in very small concentrations. It's not economically viable to exploit the uranium 233 resources because it's a rare isotope. It's found in extremely small quantities. For that reason, most of the reactors, they go for uranium 235. They do not use uranium 233. Wherein India is using uranium 233, the only reactor in the world that uses uranium 233, and we are not retiring it because we want to test it when we step into the third stage of nuclear program, that is converting thorium to uranium 233. Good. And Kamini is located in IGCAR Kalpakam. It's located in Indira Gandhi Center for Atomic Research in Kalpakam. Yes. Apsara use a production reactor. Yes, India alone uses uranium 233. Actually, there were two reactors. So one reactor was Kamini, and there was one more reactor in Ural Mountains in Europe. But then they have shut down the uranium 233 reactor because the fuel was very difficult to get. Wherein India is still running based on uranium 233 fuel. We are keeping the technology alive so that we can exploit this when the thorium is converted into uranium 233 in the third stage of India's nuclear program. Clear? All right. And then I've given you the question. You can refer your Telegram channels. Does India have atom bomb capability? Do we have capability to produce atom bomb? Please repeat fissile and fertile materials. See, simple thing. Fissile material means you can use it in nuclear reactors instantly. That is uranium-233, plutonium-239, uranium-235. All these materials that undergo fission reaction by slow thermal and fast neutrons that can be readily loaded into a bomb or readily loaded into a atomic reactor. You call it as a fissile material, wherein there are materials that have the potential to convert into some other material and then undergo fission reaction. Those are called as fertile materials. The best example is uranium-238 and thorium-232. We cannot straight away use thorium-232. We are converting it to uranium-233. So thorium-232 and uranium-238, they can be used as atomic fuel after artificial transmutation. So those are called as fertile materials. Is it clear? Shivapriya, is it clear? Yes. Whether uranium-233 is also found as a natural source, the Asiatic wild cheetah. Yes, uranium-233 is found in extremely small quantities. So that's why we are producing it through artificial means. Also, one important thing, uranium-235 is naturally found. Plutonium-239, it's not a naturally found isotope. This is produced as a byproduct of nuclear reactors. Understand? This is not naturally found, does not exist in nature. This is formed as byproduct in nuclear reactions. Similarly, uranium-233 is available in small quantities in nature, wherein we'll be producing through artificial transmutation. Clear? Okay, before we discuss about atom bombs, we'll take a small break. We'll take a 10 minutes break and then come back. The people can refresh and come back. Yes? Till then, if you people have any doubts, please drop your messages here. Yeah, can we start? We have a good question here. If plutonium is capable of undergoing fission reaction, why don't we use it directly for producing fuel rather than using it for transmutating thorium? One thing, India wants to reduce the import of uranium because importing uranium is it's costing a lot. We have been paying Canada, Russia, USA, and other countries. So if you want to have more forex reserve and if you want to reduce the import, slowly we have to gather more amount of plutonium, and then slowly we have to start using all the heaped up plutonium into thorium reserves. So first step, for 6 or 7 decades, we gather plutonium, and then we use the plutonium to produce power, and then we use the same plutonium to convert thorium to uranium-233. So it's a double bonanza. That's how it works. Is it clear? If we're going to exploit all the uranium, all the plutonium-239 only for power purpose, we cannot exploit thorium. Which country has more plutonium? No, I told you, plutonium is not found in nature. It's produced as byproduct of other nuclear fission reaction, which means probably India has a lot of plutonium left over. Even Germany has a lot of plutonium. We cannot say which country has the most number of plutonium-239. Plutonium-239 is not found in nature, so we cannot calculate it like a mineral. It's formed by nuclear fission reactions. Is it clear? Sir or madam, is it clear? Can we go to the next one? Good. To simplify your question again, uranium to plutonium. So instead of using the entire plutonium for producing power, we are going to produce some more plutonium that can be used to transmutate thorium into uranium-233. So this plutonium produces power, and this plutonium also produces power while transmutating uranium-233, and then this uranium-233 can also produce power. So instead of capping plutonium-239 here, we have step 1, step 2, and step 3. 3 different modes of power production, which is more beneficial. Do you get it? Yes. We'll go to the next one. First is Pokhran 1. That is, India tested a fission bomb, one atom bomb or one fission bomb. This was tested on 18th May of 1974, making India the 6th country to have nuclear bomb capability. India was the 6th nation in the world to have nuclear power capability. You can easily remember it because India became the 6th space power in the world to launch its own satellite using its own launch vehicle. India became the 6th country to have the power of nuclear bombs. India has so far detonated 6 atom and hydrogen bombs. So 1, 2, 3 sixes, both in space as well as nuclear reactor. 6th country to launch its own satellite, 6th country to have atom bomb, 6 detonations so far. 6, 6, and 6. Clear? The first Pokhran was performed on 18th May 1974 under the leadership of Mrs. Gandhi. And what was the impact of Pokhran 1? What was the outcome of Pokhran 1? What happened to India after Pokhran 1? Can someone say? After Operation Smiling Buddha. What was the reaction of world nations after Operation Smiling Buddha? Okay. So we did not face economic sanction immediately. We faced it after Pokhran 2. So after Pokhran 1, the world nations understood that India is using the fuel for producing atom bombs also. So other than power purposes, India is using it for atom bombs also. So following by that, we were kept under strict surveillance, especially by the American remote sensing satellites. We were kept under strict surveillance. making multiple photographs of the Pokhran area so that in future, if India attempts for a nuclear test, they can stop. That was the aim. This happens in 1974. And while the world countries were thinking that the nuclear or atom bomb era of India was over, we tested more atom bombs and hydrogen bombs in 1998. 11 May 1998, you could see in the picture, we have Dr. APJ Abdul Kalam and everyone dressed as military professionals. So what India did was, India knows that American satellites are taking photographs of Pokhran 1 and checking if there is any suspicious activity. So to fix that, what we did was, we assembled all the nuclear scientists in different locations around the Rajasthan, and then they were assembled at a single point after they were given military uniforms. So all these people, they were given military uniforms, no suspicious movements, everyone traveled through train and different, all buses and everything, they traveled to other parts of Rajasthan and they were assembled at a single point. Before assembling at a single point in Pokhran, they were given military uniforms. So, and then the scientists calculate the time through which the American satellite will pass above the Pokhran. Each day, at what time the American satellites will pass above the Pokhran and then take a photograph. That was carefully calculated. And then, whenever the satellite crosses, either the scientists will go into bunker, that is, they'll hide into the bunker, or sometimes they will perform some random military drill when the satellite is passing. So when America takes a photograph, either they'll see an empty desert, or they will see few people performing drills in military uniforms. So what America thought was, okay, they are performing an army drill somewhere in the deserts of Rajasthan by training its soldiers. That's what America was thinking. And then surprisingly, to everyone's surprise, on 11th May of 1998, we detonated 3 bombs. 2 fission bombs, that is atom bombs, and 1 fusion bomb. Keep in mind, India has capability to produce hydrogen bomb also. So we detonated 2 atom bombs and 1 hydrogen bomb, that is fusion bomb. And then this activity was surprising for many people because America, Europe, and many places, they started feeling the tremors. That is, seismic wave was recorded. So then only people understood, okay, India is performing atomic test again, and we have been cheated. Especially USA, they said it is the largest intelligence failure for them in the entire decade. 1990s, the entire decade, Pokhran 2 is the largest intelligence failure of the USA. That's what they admitted. And while all the world nations were condemning and creating a large amount of problem, and again in 13th May 1998, we detonated 2 more fission bombs. But it created a huge storm in the international politics, and in another 2 days, we detonated other 2 atom bombs, fission bombs. So which means 2 plus 1 is 3 plus 2 is 5. 5 detonations in Pokhran 2 and 1 detonation in Pokhran 1. Altogether, 6 detonations by India. 5 nuclear fission and 1 nuclear fusion. From this, 11 May 1998. This is important because 11th May is celebrated as National Technology Day. I repeat, 11th May is celebrated as National Technology Day for 2 reasons. First thing, we successfully tested fusion bomb, that is hydrogen bomb, which is more complicated. And second thing, we tactically evaded the surveillance of USA and performed a surprise bomb detonation. For these 2 reasons, and to make us feel proud, 11th May is celebrated as National Technology Day. Don't confuse it with National Science Day. This is National Technology Day. Clear? Okay, coming to the next one, nuclear fusion reaction. I'll tell a statement. You see if you are able to answer this. First one, nuclear fission reaction does not depend upon temperature and pressure. True or false? nuclear fission reaction does not depend on temperature and pressure. Nuclear fission reaction does not depend on atmospheric temperature and pressure. True or false? True. It can happen at room temperature. Okay. Nuclear fusion reaction, it does not depend on temperature and pressure. True or false? Nuclear fusion reaction, it does not depend on temperature and pressure. True or false? False. Yes, good answers. Now the question is, why is that nuclear fusion reaction requires more temperature and pressure? So I'll tell you, it requires around 10 power 7 to 10 power 9 Kelvin. A million degrees Celsius is required and a high amount of pressure is required. Why is that nuclear fusion reaction require high amount of pressure? Why nuclear fusion reaction requires high amount of pressure and temperature? Any random guesses? An endothermic reaction to fuse nuclei. Okay. So Asiatic wild cheetah says it's to fuse nuclei. Good. What happens when we bring a positive charge near another positive charge? When two positive charges are closer to each other, they'll try to repel. Correct? So similarly, when you try to fuse two nuclei and when you bring two positive charges close to each other, there's protons and protons, it creates a huge amount of repulsive force. It's impossible to fuse nuclei at normal temperature. And when there is high temperature and when there is high pressure, the mutual repulsion is overcome and then the nucleus will fuse. This is the idea. So take a look at this. The difference between hydrogen bomb and atom bomb. I will tell you. Vinisha, I'll tell you. First, observe this. Sound or ma, Sanjay? Hold on.
Nuclear fusion presents a similar picture, or rather, a mirror image. It only works with small atoms, like hydrogen, for example. The atomic nucleus of the latter consists of only one proton. If one now tries to force two of these protons together, these two would have to repel each other due to their equal charge, as in the case of magnets. When talking about atomic nuclei, this is referred to as the so-called Coulomb force. This force acts as if each of our protons had a fence around it. This happens by speeding up the atomic nuclei, and that happens when they are subjected to great heat or pressure. The more pressure is available, the less heat is needed. Sooner or later, two atomic nuclei will hit each other at such great speed that the force of the impact will overcome the Coulomb force and the protons will no.
Yeah, so that's the idea. When there's more temperature and more pressure, nucleus can fuse. And now the question is, how do we create, this is the overall reaction for nuclear fusion reaction. The question is, how do we create a 10 power 7 Kelvin up to 10 power 9 Kelvin of temperature and high pressure on Earth? Because a normal industrial flame maybe it can produce around 200 or 300 or maximum up to 1000 degrees of Celsius. How we are going to create 1 million degrees Celsius and how we are going to produce high pressure? Any answer? How is it possible? By fission reaction. Good. That's the key. So, Vinisha, you were asking about hydrogen bomb and atom bomb. So atom bomb, uranium 235 or plutonium 239, it's split up into different atoms like barium, krypton, xenon, strontium, and it produces a lot of neutron with heat energy. This is nuclear fission reaction. If you're going to use this reaction in bomb, it's called as a fission bomb or atom bomb. Whereas if you're going to use this reaction, it's called as a fusion bomb or hydrogen bomb. Now, as you people told, it's impossible to create this much of temperature by man-made methods. It's extremely hard. Right now, we have newer technologies. For example, the tokamak reactor or the International Thermonuclear Experiment, it is right now producing this much of temperature, but it's extremely hard to produce this much of temperature on the surface of Earth. For this reason, we'll be producing fission bombs. Fission bomb produces a lot of energy, and that energy will be used for fusion bombs. So that is the reason. See here, we detonated 2 fission bombs, and along with fission bombs, we detonated 1 fusion bomb. That is 2 atom bombs exploding, and it creates a lot of heat and temperature, heat and pressure, and that is used for a hydrogen bomb. Is it clear now? To the person who asked? Vinisha, is it clear? First, we detonate an atom bomb. Atom bomb produces a lot of temperature and pressure, and that is being used for fusing nuclei. That is, we call it as fusion bomb. Sir, will atom bomb produce this much of temperature? Understand, atom bomb produces extreme high amount of temperature and pressure, which is unimaginable. For example, I'll tell you a basic example. There is a famous documentary by a veteran from World War II. He was made to stand near the shores of Hiroshima. When America dropped the atom bomb for the first time on Hiroshima, they were made to stand in a boat somewhere located a little away, a few kilometers away from the Hiroshima coast. That was a time where the human race has not witnessed the power of atom bomb. We have no idea how much destruction an atom bomb can produce, because we know that it will produce destruction, but we have never seen on a live scale the amount of destruction that will be produced by an atom bomb. So the instruction given to these soldiers, that was, when we drop a bomb, there will be a flash. And when you see the flash, don't look at it. Try to cover your face like this. Cover your eyes with your arms. This was the only instruction given to them who are standing few kilometers away from Hiroshima. Good. The bomb is dropped. It creates a mushroom cloud. It creates a huge flash with a lot of temperature and pressure into the Hiroshima city. And when these people receive the flash, most of them, they are thrown into the water because of the shock waves. And few of them who were just covering their hands like this, what they saw was their blood, their bone and nerves with naked eyes. Imagine a live X-ray. Imagine if you cover like this and if you're able to see what is present inside your body, the circulation of blood, the nerves, the arteries and the bones and everything, if you could see with naked eyes, that's the amount of impact a single atom bomb will create. It will emit all the electromagnetic waves, starting from radio, micro, infrared, visible, ultraviolet, X-rays, gamma rays. Everything will be emitted in extremely high amount of dosage. Along with that, a lot of heat energy is produced, and then it causes huge amount of genetic mutation, destruction to life and everything. The impact of atomic bomb is devastating, one of the most nasty bombs that we have ever created. So that's the reason atomic bombs are exploded, and that heat that is close to 1 million degrees Celsius is used for hydrogen bombs. That's how it works. Good. What is true? This is neutrinos. Neutrinos, all these are subatomic particles. Neutrinos, baryons, leptons. They won't ask these many technical details. 4 hydrogen fuses to form 1 helium. You can remember it that way. Good. Yes. With that, our nuclear physics is coming to an end. We have capability of producing atom bombs as well as hydrogen bombs. Good. Okay, so we have around half an hour left over. We will start with the basics of biology. As I told you, 2 choices. You people wanted to get few information about static biology portions. So today we'll be dealing with static biology, half of the static biology, and tomorrow, the next class, we'll be finishing the static portion and then starting with the current affairs. I think, in my guess, we'll be completing close to 50% of static biology portions. Good. And after this, notes writing will be minimal for today's class. You can write on all single line explanations. I would like to tell one thing in advance. The static portion which I'm teaching now, it cannot replace your NCERT reading. This is basically a Kickstarter. Is there anyone from a biology background here? I think I asked it earlier. Anyone from biology background? Say any physicians or people who are from biology background? Anyone from biology background? MBBS graduate, okay. We have a physician here, okay, good. So Vinisha, few terms in this biology part, I'll be giving only layman's definition. So from the technical side, for a physician, it might look like a oversimplified definition, good. Please bear with me in that aspect. If time permits, please tell NCERTs to read. Yes, by end of the class, I mean in the next class, I'll be telling you what to read and what not to read in NCERT. And how India tested atom bomb with controlled explosion. No, we did not control atom bomb in a controlled explosion. We kept it under the bunker in a desert region. We buried the atom bomb deep underground. It was not a controlled explosion. Yes, Archana, by the next class when I finish, I'll be telling more about it. Starting with the first thing, let's talk about how organisms are classified. There are different classifications for organisms. First, we are starting with two things. One is prokaryotes. The other is eukaryotes. What is meant by prokaryote and what is meant by eukaryote? First, this tells you the difference between a plant cell and an animal cell. This is animal cell and this is a plant cell. I'm going to keep it this way so that we can easily browse through different topics. First, we were talking about prokaryotes and eukaryotes. The first, prokaryotes, you can write all single line definitions. Organisms that do not have well-defined nucleus are called as prokaryotes. Take a look at this. There are well-defined organelles here. We have mitochondria, we have endoplasmic reticulum, nucleus is defined, lysosome is defined, centriole is defined. So all these are well-defined. So this is an example of eukaryotes, where in prokaryotes, certain type of bacteria And unicellular organisms, they are prokaryotes. Prokaryotes means no well-defined cell organelles. Eukaryotes, organisms with well-defined cell organelles. Eukaryotes, organisms with well-defined cell organelles. Organisms with well-defined cell organelles. Now we are coming to the other thing, that is five kingdom classification. Organisms, they are placed in five kingdoms. One is Monera. Then we have Protista. Then we have a kingdom called as Animalia. Then Plantae. Then we have fungi. Five kingdoms. We are placed in the Animalia kingdom, and then plants are placed under Plantae kingdom, fungi are placed under fungi kingdom, and there are prokaryotes are placed here and eukaryotes are placed here. Monera is generally prokaryote. Rest of them are eukaryotes, and especially this is unicellular eukaryote. Five kingdom of classification, and this is not foolproof or false free. It's not a future-proof method of classification, because virus is not organisms like virus, virion, prions, they are not placed anywhere in the five kingdom of classification. That's given as one demerit of five kingdom of classification. We have many organisms that cannot be placed in any of these five kingdoms. And then after kingdom, we have phylum, genus, species, class, order. It goes on and on and on. We are not dwelling into detail about it. Coming to the next part, cell organelles. I told you there are different organelles inside. I'll be giving you basic definition to all these. I'll be sharing these mind maps with you by end of the class. I'll give access to all of these mind maps. First, we'll start with cell wall. The first cell organelle that we are dealing is cell wall. Do we have cell wall? Can someone say if we have cell wall? That is there cell wall in animal cell? Anyone? Is there cell wall in our cells? Any random assumptions? Okay, between yes and no. Good. So cell wall, it is outermost protective layer of a cell. It is not present in animal cells. It's present only in plant cells. Write down. Cell wall is present only in plant cells. It is the outermost protective layer. Single line I'm saying. Outermost protective layer. Cell wall gives rigidity to the cell. It's absent in animals. Cell wall is absent in animals. It's a rigid cover generally made of cellulose. Don't write everything. Cell wall, outermost protective layer, present only in plants, not in animals. Second one is cell membrane. We have cell membrane. Cell membrane is the outermost envelope of the cell. Outermost envelope of the cell is called as cell membrane. So this basically separates the contents of the cell from the environment. So you call it as cell membrane. You could see here, outermost is called as cell membrane. Where in plant cell they have cell wall, a rigid wall. We have only cell membrane. The outermost protective envelope is called as cell membrane. Coming to the next one, cytoplasm. You can draw a rough diagram here. If you take the cell, anything that is present, anything that is present inside the cell membrane, excluding the nucleus. This part is called as cytoplasm. Cytoplasm is between cell membrane and nucleus. You can write one line. Between cell membrane and nucleus. Okay, Sri Lakshmi is asking cell membrane is not in plants. No, plants have both cell wall and cell membrane, wherein we have only cell membrane. So cytoplasm, it is present between the cell membrane and the nucleus. That is called as cytoplasm. Cytoplasm has a lot of things inside, and then we have nucleus. What is special about nucleus? Nucleus is called the control center of the body, control center of the cell. Then there is one more thing called as protoplasm. So what is the difference between protoplasm and cytoplasm? Simple. Everything inside the cell membrane together, it's called as protoplasm. So protoplasm is basically cytoplasm plus nucleus. Protoplasm is cytoplasm plus the nucleus. Basically everything present inside the nuclear membrane is called as protoplasm. So don't confuse protoplasm with cytoplasm. Protoplasm plus cytoplasm. And now coming back to cytoplasm, we have multiple components. First, see, cell wall, and then cytoplasm is between nucleus and plasma membrane. Nucleus is separate. Right now we are dealing only about cytoplasm. First, we'll start with endoplasmic reticulum. Endoplasmic reticulum, it is here, all ribbon-like structures present inside the cell. It's called as endoplasmic reticulum. We have two types of endoplasmic reticulum, smooth endoplasmic reticulum and rough endoplasmic reticulum, RER and SCR. Smooth endoplasmic reticulum and rough endoplasmic reticulum, two types. You can draw a simple flow diagram. Smooth endoplasmic reticulum and rough endoplasmic reticulum. Now the functions of smooth endoplasmic reticulum and rough endoplasmic reticulum. Rough endoplasmic reticulum, it is related to protein synthesis. Remember, rough endoplasmic reticulum is related to protein synthesis, wherein smooth endoplasmic reticulum, it is related to synthesis of lipids. Fats, cholesterol, everything is called as lipids. So, two endoplasmic reticulum. So, the reason why it's called as rough and smooth is rough endoplasmic reticulum, it will look rugged. It will have a lot of ribosomes attached on it. So, it will appear dotted and it will appear like a sandpaper. That's why we call it as rough endoplasmic reticulum. You could see here, rough endoplasmic reticulum. On the surface, there'll be small dots. It appears there are small projections on the top. So you call it as rough. The other one is smooth. The functions is I told you. This is related to production of lipid. This is related to production of proteins. Next is vacuoles. Next is vacuoles. Keep in mind, we are talking about only the cytoplasms, cell organelles present in cytoplasm. Vacuoles. Do we have vacuoles? Or are there vacuoles in the plant or are there vacuoles in the animal cell? Can someone answer? Yeah, we ran out of battery, sorry. So vacuoles, it's extremely small in animal cell. Vacuoles are extremely small in animal cell, where in plant cell it's huge. Vacuoles are places of food and liquid storage. You could see the vacuoles are large in animal cells. So you can write vacuoles are large in animal cells. Vacuoles, they are large in animal cells. And in few animals, vacuoles are small. Only the humans. Few animals have vacuoles which are extremely small. So vacuoles are large in plant cell, extremely small in animal cell. They are places of storage. They are called as storage sacs. They are called as storage sacs. Good. Coming to the next one. After vacuoles, we are talking about Golgi apparatus. The next is Golgi apparatus. They have wide variety of function, but write down storage, modification, and packing. They are used for storage, and they sometimes modify things, and then they pack things that are produced by endoplasmic reticulum and everything, and it's sent to different parts of the body. So storage, modification, and packing. Storage, modification, and packing. Vinisha, yes, as per the NCERT, there are few animal cells that has extremely small amount of vacuoles. Vacuoles are appearing in a microscopic scale. Few animal cells, not every animal cell, few animal cells. And then coming to the next, that is lysosome. Lysosome is important because we had news about lysosomal storage disorder in recent times. Lysosomes, they are called as suicidal bags of cell. They help in digestion of cells. When cell is repaired, or when a cell is damaged, or when a cell is has completed its life cycle, then it is digested using enzymes present in lysosome. So lysosomes are called as suicidal bags of cell. Lysosome hyphen digestive enzymes. They are digestive enzymes. which means if lysosome is not functioning properly, the cell will not digest properly, and there will be a lot of toxin accumulation. Now coming to mitochondria. What is the other name given to mitochondria? A familiar statement. Yes, in plant cells, vacuoles are big because plant cell stores a lot of fluids and in the form of vacuoles. Inside vacuoles, we have a lot of fluids, basically liquids plus gases. Powerhouses, good. Mitochondria is called as powerhouse of cell because it produces adenosine triphosphate, the energy currency. ATP, adenosine triphosphate, is produced by mitochondria. And what is special about mitochondria? Which part of the cell has DNA? Which part of the cell has the DNA, deoxyribonucleic acid, that is the unit of inheritance that carries all our traits. Where do we have DNA? Nucleus. Yeah. So most of the DNA, it's found in nucleus, and other than nucleus, we have DNA in mitochondria also. That's called as mitochondrial DNA, also called as maternal DNA. So mitochondria has mitochondrial DNA. Which means there is nucleus inside, there is DNA inside the nucleus, and also there is some nucleus inside the mitochondria. This is called as mitochondrial DNA. Sometimes it's called as maternal DNA. The reason is when sperm and egg fuses during the human reproduction, the sperm transfers only the nucleus. That is, only the nucleus is transmitted from the sperm, wherein the mitochondria to the fetus is carried over from the mother. For this reason, if mother has any disease, genetic disease, especially related to the mitochondrial DNA, it will be carried over to the fetus. That's why it's called as maternal DNA. Many genetic diseases, it is carried over from the mother to the fetus or to the future generations through mitochondrial DNA. That's why we have the concept of three-parent baby, where two women and one man are involved. That is sperm, nucleus from one male, and one female gives the egg. And if the mitochondria in this egg is not healthy, if it has some genetic diseases, then one more female will provide a healthy mitochondria. And then these three will be fused together, which means nucleus from a male, egg, most of the egg part from a female, and only the mitochondrial part from another female. So three parents are involved indirectly, and then the offspring produced is healthy because the mitochondrial DNA is replaced with a healthy mitochondrial DNA. So this is called as three-parent baby. We'll discuss about it later. The mitochondria has its own set of DNA and also it produces adenosine triphosphate. Remember. Coming to the next one, plastids. Next is plastids. So plastids are present only in the plant cells. Plastids are present only in the plant cells. Plastids are present only in the plant cells. For example, I'll give you three examples. We have chloroplast, that is associated with photosynthesis. Then chromoplast. Chromo means color. Anything that gives color to the cell, that is a fruit or a flower, if it's going to give color, we call these pigments as chromoplast. And then we have leucoplast. Leuco means it is colorless, which means it's associated with storage. Leucoplast is associated with storage. chromoplast is associated with color, chloroplast is associated with photosynthesis. These are examples of plastids, and plastids are present only in plant cells, not in animal cells. Clear? And then, coming to the next part, we are going to read about nucleus. Next is nucleus. So nucleus, it contains chromosomes that contains DNA and proteins. Chromosomes contains DNA and proteins, deoxyribonucleic acid, that is unit of inheritance or carries the traits. And also understand the chromosome won't be visible all the time. Chromosome appears only during cell division. We can see the chromosomal division structure only during cell division. So what if there is no cell division going on, sir? Then there will be a thread-like material called as chromatin material. Generally the cell has chromatin material. Chromosomal structure won't be visible, and only when the cell is undergoing cell division, chromosomes will be visible. And this chromatin material or chromosome contains both DNA and protein. Achana, about plastids. Plastids are present only in the plant cell. So there are different types of plastids. Chloroplast, anything that helps in photosynthesis, is called as chloroplast. And then we have chromo. Chromo means color. The one that gives color to the fruits and flowers, the pigment is called as chromoplast. And then we have leucoplast, that is colorless and helps in storage. So these plastids are present only in plant cell. Animals do not have plastids. Clear? And then chromosome has DNA and protein. So these are the important cell organelles. We are done with the cell organelles. We have some time left over. Bear with me for another 5 minutes. We'll complete biomolecules and then wind up the class, so that it'll be easy to continue from the next class. Can someone tell me what are the important macromolecules that we are supposed to intake? We have macronutrients and then we have micronutrients. Chromatin material, Vishwapriya, inside nucleus, you will have thread-like structures. Those are called as chromatin materials. Once it undergoes cell division, the chromatin material will form chromosomes. Have you seen the chromosomal structure that is generally displayed in school times? You have it in books. There are different types of chromosomes. We have acrocentric, telocentric, different types of chromosomes that will appear like this with a centromere. This is how the chromosomes will be appearing. And then sometimes it will go to the end. You call it as acrocentric. If it is this way, that's called as acrocentric. If it is located at the end, you call it as telocentric. There are different classification of chromosomes. You can read more about it in NCERT basics. Since I'm giving only the superficial basic introduction, chromosome has DNA and protein. Remember it. Clear? Chromosomes has DNA and protein. Okay, carbohydrate, proteins and fats. Talking about biomolecules, we have different biomolecules, and most importantly, we are supposed to take carbohydrates, fats and protein on a regular basis. So that's why people say we are not supposed to cut carbohydrates all of a sudden. So people say, I'm going to cut on rice, I'm going to cut on chapati, I'm going on a pure fruit diet, I'm going on a pure vegetable diet. Don't make these attempts, because your brain needs energy. You will run into depression if you are going on nil carbohydrate or nil sugar. You are supposed to take sufficient amount of carbohydrate. So carbohydrate, proteins and fat is necessary in descending order. We need more carbohydrate and then protein and then fat on a daily basis. So first let's talk about carbohydrates. When you see carbohydrate, remember sugar, because carbohydrates are made of saccharides. That is, they are made of sugars. And based on the number of sugar molecules that forms the carbohydrates, we have different classification. We have monosaccharide, disaccharide, trisaccharide, oligosaccharides. There are different classifications. First, write down one basic definition. Carbohydrates are hydrates of carbon. Carbohydrates, they are hydrates of carbon, which means they have a general formula CX H2OY. Best example is C6H12O6. These are examples. So they are called as hydrates of carbon. They are built of saccharides. That is, they are built of sugars. Good, they are built of sugars. And based on the number of sugar molecules that forms the carbohydrates, we have different classifications. For example, if it is made of single sugar molecule, you call it as monosaccharide. The best example is glucose, made of one sugar molecule. Then we have oligosaccharide. What is mean by oligosaccharide? If a carbohydrate is made of 2 or up to 10 sugar molecules, you call it as oligosaccharide. And if it exceeds 10 sugar molecules, you call it as polysaccharides. All these falls under carbohydrates. Mono is single sugar. Oligo is 2 up to 10 sugars. For example, oligo has disaccharides. Best example is lactose. The milk sugar that we take, it's called as a double sugar or disaccharide. Those fall under oligosaccharide. And cellulose, that forms the cotton thread or outer layer of the many plant cells, they fall under polysaccharides. Now, given examples in the NCERT, you can go through it. Glucose is example of monosaccharide. Lactose is example of oligosaccharide. And starch is example. Starch or cellulose is example of polysaccharide. I've given in the mind map. We have monosaccharide, glucose, fructose, ribose, and galactose. And then we have oligosaccharides. And then we have polysaccharides. Starch, cellulose, glycogen are example of polysaccharides. Then next, let's talk about proteins. Please stay online for another 2 or 3 minutes. We'll complete the macromolecules and then we'll wind up, so that we get a continuity in the next class. Next, let's talk about proteins. So proteins are made of dash, a familiar statement that we have learnt in school time. Proteins are built of dash. Proteins are built by, do you remember what are proteins made of? Amino acids. Good. So proteins are made up of amino acids. So first you have to understand what is meant by amino acid. It says amino and then acid, which means it has 2 groups. That is, it has a nitrogen group, that is NH2, and then it has an acid group, COOH. These are amino acids, and multiple amino acid joins to form proteins. Now, there should be some glue that connects these amino acids, correct? These amino acids, they have to be connected using something. That's called as a peptide bond. Peptide bond. So, this peptide bond joins the amino acids together and forms proteins. So, that's why proteins are called as polypeptides. Proteins are polypeptides. Multiple amino acids and are joined together by peptide bond and it forms proteins. That's why it's called as polypeptides. Good. Now let's talk about fats. Fat is also important. We are supposed to take it in limited amount because first thing, fat is the storage, emergency storage. When we run out of energy, generally fat is converted into glucose. For that reason, fat is important, and also It forms adipose tissues. The protective tissues that's present in the human body, adipose tissues, it's formed by fats. Fats are triglycerides. Fats are triglycerides. Fats are triglycerides. That's because it has 3 fatty acid chain. Sorry, 3 glycerides. And it's an ester of 3 fatty acid and 1 alcohol. In fact, it's alcohol glycerol. Sorry. For this reason, fats are called as triglycerides. Also understand, fats is it's a part of lipids. We'll discuss about lipids in the next class. Lipid is the umbrella term. We have different lipids like glycerol lipids. Fat is a type of lipid, and fats are called as triglycerides because they have 3 fatty acid chain along with 1 alcohol glycerol. They form adipose tissues. Whenever you come across this term in newspaper, adipose tissues are tissues that stores fats. In fact, 2 important things about adipose tissues. First thing, it acts as insulation. It acts as temperature insulation, and most importantly, it acts as protective layer. For example, we have adipose tissues here, and it protects all the internal organs like kidney and everything, and even the eyeballs. They're properly placed in the socket and then protected by adipose tissue, which means even fat is required. Fat is also an essential macronutrient. Fat, Archana, is it clear now? Fat helps us to form adipose tissues. The protective layer around our eyes and the one that protects our internal organs, it is called as adipose tissues. And if someone has a lot of adipose tissues, then we have the tire-like appearance around the tummy. That's because more adipose tissues on the sides. This tire is formed because of adipose tissues. Good. Adipose tissues is related to fat deposit. Good. So that's all about macromolecules, and then we have to discuss about micronutrients. I'll complete this. So micronutrients we are not going to take up in the class because it's simple. Vitamins and minerals are micronutrients. You can read it from this. What are vitamins? Vitamin A, B complex, C, D, E, and K. So what happens when we run short of vitamins? We have different diseases. Vitamin A, when it is deficient, it leads to loss of vision. Vitamin B1, very scurvy, rickets. Starting from class 8 till class 12, they would have given in different parts of NCERT. I will send it through the material that I will be sending. You can go through it and do a self-study. Vitamin, it is generally taken through fruits and food. If we are running short of vitamins, we'll have multiple disorders. And then minerals, iron, zinc, molybdenum, these are the minerals that are required. There are many minerals that is required in varying quantities. We are supposed to intake minerals also. That's all. So this is about biomolecules. We'll continue in the next class, starting from different endocrine glands, exocrine glands, and everything. Good. Is there any doubt till this? Do people have any doubts? Can we wind up? Tell me if you people have any doubts. I'm watching your messages. No doubts for now? Okay. Yes, thank you, Mahesh. So next class, mostly it will be somewhere close to 2 hours and 45 minutes. I'm telling in advance because we have to complete the static portion and then take up the current affairs. I won't extend up to 3 hours, but maximum 2 hours and 45 minutes it will be. Be prepared. Good. We'll be finishing the 4 macro topics by the next class. Did not understand the meaning of fatty acid chain? I'll be repeating the fatty acid chain in next class because it's individual topic. We'll talk about fatty acid chain. Don't worry, Archana. Shivapriya, you want to know about cytoplasm and protoplasm? Okay. Other people, you can leave the meeting. Thank you very much for cooperating. I'll see you in the next class. For the people who wanted to watch this, see, this is the nucleus. Sorry, this is the cell, and this is the nucleus. This is the nucleus. And this part, this blue colored portion between the cell membrane and the nucleus. This is called as cytoplasm, which means we have excluded the nucleus. Good. So protoplasm is cytoplasm plus the nucleus. Everything that is present inside the cell membrane, it's called as protoplasm. Everything together, you call it as protoplasm. Anything that is present inside the cell. Is it clear now? Shivapriya, is it clear? Yes. Okay. So then we'll wind up the meeting for now. Thank you very much. I'll see you in the next class. Good night. Yes, thank you.